Hello everyone. 9 here broadcasting to myself, I guess. It's 2025, May 6th, Tuesday, right? Today I'm pulling out a really interesting one from the archives. A bit of a thinker, you know? Let's dive in. Okay, so this paper. Let's get the details down first. The title is Evaluating Explanations by Explanatory Virtues Framework. For Mechanistic Interpretability, the goal is transforming on. Folksing, it's long, right? Got that noted. So, what's the big idea here? Well, there's this field called Mechanistic Interpretability, for short. Its whole goal is to figure out how these complex AI neural networks actually tick on the inside. Like really understand the causal workings. Sounds super important, right? Especially with AI everywhere. But here's the problem the paper points out. We have all these methods and need for generating explanations, but we don't really have a universal way to judge them. Like, how do we know if one explanation is actually better than another? Sometimes different researchers look at the same AI model and come up with explanations that totally contradict each other. Which one is right? Hard to say. And worse, sometimes an explanation might seem plausible, but it turns out to be incomplete or just plain wrong. The confabulation, they call it, gives you the illusion of understanding, but you don't really get what the model is doing. Checks. You need some solid ground rules. So this paper introduces what they call the Explanatory Virtues Framework. It's trying to answer that fundamental question. What makes a good explanation? And it does this by drawing on ideas from the philosophy of science. Right, bringing philosophy into AI interpretability. It looks at 4 perspectives: Bayesian, Kuhnian, Tutetan, and Nomologicity. These perspectives give us a set of explanatory virtues, properties that good explanation should have. Things like accuracy. Obviously, does it fit the data? But also simplicity, is the explanation easy to grasp, not overly complex? And fruitfulness, does it help predict new things we haven't seen yet? Consistency, does it contradict itself? Falsifiability, can we actually test if it's wrong? Hard-to-Varyness, meaning we can't just easily tweak an explanation to fit any new data that comes along. It should be robust. And others like Unification, does it connect different phenomena together? And Nomologicity, does it appeal to general laws or principles? The paper then uses this framework to look at existing methods like Clusian sparse after clutters associations, causal circuit analysis, and something called compact proofs. It finds that while current methods often focus on accuracy, they sometimes neglect other important virtues. While they aren't always great at finding simple explanations, or explanations that unify different behaviors, or ones that uncover general nomological principles about neural nets. Why does this matter for, everyday life? While understanding AI better through good explanations is key. Think about machine translation. If an AI translator gives a weird out but a good explanation, it could tell us why it made that specific error, helping us fix it, making translations more reliable, especially for tricky languages. We'll consider chatbots and dialogue systems. You want them to be helpful, right? Understanding their termisms helps ensure they aren't generating biased, harmful, just plain nonsensical text that builds trust and accountability. And what about information extraction or text summarization? Imagine the AI summarizing critical medical reports or financial documents. You need to be damn sure it's extracting the correct information and summarizing it accurately. Good explanations help verify that process, making sure the AI isn't hallucinating or missing vital points. The paper suggests focusing research on these neglected virtues, like we need a clearer definition of explanatory simplicity. We should aim for explanations that unify different aspects of AI behavior, rather than just explaining isolated bits. And we should look for the nomological principles, the general rules governing how these networks learn and operate. It's like moving from just collecting observations, or cataloging rocks, as they put it, towards building a real, predictive science of AI in general. It makes a lot of sense. You need reliable ways to evaluate if our understanding of AI is genuine or just an illusion. This framework seems like a solid step in that direction. Okay, that was a dense one, but super interesting stuff. Next, into the next segment.